Okay, can you see the slides? On energy gap? Alrighty, good. Okay, let's get started. So today we're gonna move on to energy gap. All right, so as usual, before I move on to the new topic, I usually do this. I call this as challenge what you have learned. And if you look at these questions, we have discussed about the top two yesterday before we move on with our lecture yesterday. So for today, let's challenge on what we have learned on the question 3 and 4. Okay, let's discuss before we move on to our energy gap lecture today. So yeah, why do we need to dope our semiconductor materials again? Why doping? Let's do a bit of recap. Why do we need to dope our semiconductor? As usual, you can unmute yourself. You can write down in the chat box. Control conductivity, yep. Alter conductivity, yep, same. So clear, right? Modify conductivity, yes, another way to put it. Good, so it's clear. Alter conductivity, modify, change conductivity to your desired need, right? So depending on what do you want to get eventually from your semiconductor materials or from your semiconductor devices. Because eventually your semiconductor devices will need to operate with, say, 10 to the 14, and some may need 10 to the 18. Some may even need intrinsic semiconductor to be in the device. So we have discussed a little bit about PN junction yesterday as a brief introduction. And also we have covered a little bit on PIN or PIN, where you sandwich a layer of intrinsic where you undope or you don't dope between a P layer and an N layer, right? So you can either have a PN junction or PIN junction. So you're going to see later on, why do we need to have PIN and why do we have to have PN? So what is the advantages of each architecture, junction architecture, if you like. So then question number 4, how do we do that? How do you dope? What do you actually do to dope your silicon, for example, in this case? So anyone? How do we do the doping? Physically, what do we do? Let me browse through the name. Kavina Cynthia. How do we do that? Kavina, can you write it down? Okay, Mushfiq said add group 3 or group 5 elements with group 4 elements. So in this case, if you're talking about silicon, then silicon is from group 4, and silicon is the host atom or the host semiconductor or host lattice. So you can either add group 3 or group 4 or group 5 into the silicon lattice, right? So if you add group 3, it's gonna be p-type or n-type for silicon. Say group 3. All right, so you're gonna make it p-type from group 3, and on the other hand, if you use group 5, you're gonna make the silicon n-type, right? P is positively charged, N is negatively charged. So give me some examples of dopants from group 3. What are the examples of dopants from group 3 or group 13? Boron, yeah, boron is a common one. You may also use gallium, for example. So if you look at semiconductor industry, solar cell industry now, they used to use boron dope silicon for p-type wafer to fabricate solar cell, and now they're slowly moving into gallium dope. because it's more stable in terms of solar panel performance in the field. When the panels are introduced to the field, then it's subjected to fluctuation of temperature, heat, moisture, and some other parameters. So they found that gallium is more stable than boron doped semiconductor or boron doped silicon. All right then. So how about group 5? What are the dopant atoms that you can use from group 5 to make the silicon more negatively charged or more n-type? Give me some examples. N-type. Example of atoms from group 5. What are they? Anyone? Right, arsenic. Yep, arsenic. What else? One is arsenic. Anything else? Phosphorus. Yes, phosphorus. Give me another one. The top 3 common, yeah, antimony or SB. Okay. So what's actually happening during the doping process is we incorporate the dopant into the lattice, Haziq said here, and then it's going to be ionization as well. Ionization process, and said by Kavina as well. Ionization is going to take place after the doping or during the doping in order to electrically activate the dopants. So what do you think will happen if you incorporate the dopants into the lattice, but you don't electrically activate the dopants? What do you think would happen? What's happening to the dopants then? Kalau kita activate dia, if you don't activate the dopants, so what's going to happen to the silicon? Any ideas? What do you think will happen? They become dormant. Okay, dormant. Okay, so if they become dormant, then is it a good thing or a bad thing? What do you think, Haziq? They don't do anything. They're just sitting there idling. So it's bad. Okay, why is it bad? Why do you think it's bad? Anyone? Well, Haziq, why do you think it's bad? They are there in the lattice, but they are dormant. They are idling. They are just sleeping. They're not doing anything. So does it change? Does it alter the conductivity of the silicon then? Because we want to alter the conductivity, right? So do we get any changes in conductivity then? Because they cannot become carrier. They cannot become carrier, and instead they become defects. Can they become defects? They are there in the lattice because we want to dope, but then they are not electrically active, so they are just sitting there idling. They're not contributing to improve the conductivity of your host atom, in this case silicon, so they eventually become defects, right? And defects are bad in our semiconductor. Alrighty, good. So let's move on. Today we're going to look into a couple of things in energy gap. So we're going to look into the band structure of a crystal. Then we're going to see what is band gap actually. So we'll discuss a little bit about band gap of in the case of semiconductor, in the case of metal, in the case of insulator. So you have got the magnitude difference, or you've got the the feel of how big is the difference between the gap or the band gap of 3 different primary types of material that we've discussed before. Effective mass of electrons and holes in the lattice, band diagram or EK diagram, energy on the y-axis and momentum on the x-axis, direct and indirect band gap semiconductors, and what's happening on the conduction of metals, semiconductors, and insulators. And then we're going to also look into temperature and doping dependence of band gap, right? Hold on, someone is joining. Okay, so we've discussed a little bit on the band structure of a given material. So we still need to find out about the detail of energy levels in terms of which are occupied, which are empty, which are partially filled, and so on, and completely filled, right? Empty bands, if you talk about empty bands, they don't contain electrons, and therefore, if you don't have electrons, they don't have contribution to electrical conductivity of the material. So we've discussed briefly about the metal, about the semiconductor, and also the insulator, right, in terms of their band structure. So let's look into the details of this. What is partially filled band and what is completely filled band? So if we talk about a partially filled band, that means the band contains electrons as well as an unoccupied energy level. So you have a mix of both electrons, presence of electrons, and unoccupied energy level as well. So the unoccupied energy levels enable carriers to gain energy when it's moving in the electric field. So electrons in the partially filled band do contribute to the electrical conductivity of the material. So examples of semiconductor or the material in the periodic table with partially filled band are sodium and potassium, right? Sodium and potassium have these properties. On the other hand, if talking about completely filled bands, they contain plenty of electrons, but then since they are completely filled, so your electrons are not free and not wandering around and contribute to electrical conductivity of the material. So then what is band gap? So band gap, so we have discussed about the band gap of silicon of 1.1 and then zinc oxide 3.3, and then insulator, say you said up to 10 electron volt yesterday, and diamond is 5.5. So what is actually band gap? So band gap refers to energy required for us to excite an electron from valence band to conduction band. So it is the energy required. So you can see here on the y-axis, if you look at this band diagram, so valence band sits at the bottom and conduction band sits on the top. So there's a gap in between that we call forbidden gap or band gap. So they are equal. Electron energy on the y-axis. So if you're looking on the vertical axis or on the y-axis, it represents the energy required for us to excite the electron in the valence band, right, into the conduction band. So it has to cross the forbidden gap or the space in between, and that is called the space in between, or the forbidden gap in between is called band gap, right? So if you talk about silicon, for example, then that means since the band gap of silicon is 1.12, let me write it down, hold on. Okay. So the band gap of silicon is 1.12 EV, electron volts. So that means we need to supply 1.12 electron volt of energy, or you can also convert into joule, in order for us to excite a valence electron from the silicon into its conduction band, from the valence band into the conduction band, for it to conduct electricity more readily, okay? So that's the amount of energy required. So what do you think will happen if, for silicon, if you supply an energy of 0.8 electron volt? What's going to happen to the valence electrons? Any idea? So we know that you need to supply 1.12 electron volt in order for us to excite the valence band electron into the conduction band. So then what's going to happen if you only have like 0.8 electron volt of energy to do the excitation to the silicon? What's going to happen in the silicon? What do you think will happen? Anyone? Hazwani? Nurul Hazwani, what do you think will happen? If you supply 0.8 electron volts to silicon, it won't excite. Okay, you said it won't excite. Any other opinions? How about Raihan? Raihan Shamim. Raihan Shamim, right? Shamim or Shamimi, is it? Let me look at his full name. Ah, Raihan Shamimi. I look at it halfway now. So what do you think, Raihan or Shamimi? Do we get excitation at all? Can we excite halfway and it goes back down to the valence band? What do you think? Raja Saleh, what do you think? Just share your opinion, that's fine. It's okay. Do we get excitation at all? No idea. Just as you said, electron can't be excited, okay. So a number of you said it cannot be excited, right? So yeah, that's the correct answer. So you cannot excite valence electron into the conduction band of silicon, which requires 1.12 eV. Okay, Ryan said electron not excited. Okay, so no conduction happens. Alrighty. Yeah, you need to cross with an energy of 1.12, but then you only have 0.8, so there will be no excitation at all, right? Just like you can imagine like this. If I'm now staying in Permatang Pao in the mainland of Penang, and then I pump up or I fuel up my car, say what, RM3. So I just use RM3, for example, to fuel up my car in order to get to USM. So will I reach USM while crossing the bridge? Cannot, right? So I'll probably just go to kilometer number 5, and the bridge is like 13.5, and the distance of my house to USM is like 18 kilos, and I'll probably just survive until kilometer number 3 or 5 km and dead over there, right, by the side of the bridge, waiting for help, right? So it will not be enough. Okay, so there will not be any excitation at all. You won't be able to cross Penang Bridge with RM3. Or for example, if you talk about touch and go, you need to cross like $5.60 or $4 something now. So you only have like RM3 in your touch and go. So your gate won't open, right? You just touch and it won't open, and you cause somebody else at the back to be angry at you, to be mad at you, because you caused a delay in the traffic, right? So it won't happen. So there's no excitation at all. So on the other hand, so if you need to supply 1.12 electron volt for your silicon, for your valence electron to cross into the conduction band, but you supply 1.4 electron volt to the electrons. So will there be any excitation in this case? What do you think? So you need 1.12, and you're supplying 1.4 electron volt. All right, so all say yes. So I need $4.70, for example, to cross the bridge with on my touch and go, and then I have like $50. Of course, I can cross, right? I can even go beyond USM. I can go to Balik Pulau or Feringhi or Teluk Bahang to enjoy the scenery or something. So I can. So the excitation will take place. So you have, so if talking about 1.12 and 1.4, so that's a difference of about 0.3 eV. So you can cross and you can excite the valence electron. What's going to happen to the next 0.3 eV of energy? What do you think will happen? So you're not supplying extra, you have extra fuel, so you have extra 0.3 electron volt of energy. So what's going to happen to the extra energy? Kinetic energy. All right, is it kinetic energy, Mushfiq? Any other ideas? We're going to learn this one later on, but just some, preamble if you like. So if you have 1.4, so if I draw on this, so you just need, okay, this electron just need 1.12. Thermal after interaction with electrons. Heat, yep, good, yes. Thermal, yes, you're there. So you need 1.12. Oops. So if I can draw this, you need 1.12, right? So to just cross the bridge or just cross the forbidden gap from H to H, from valence band H to conduction band H, you just need 1.12 just right, just right to be able to cross, to be able to excite a valence electron into the conduction band. So if you have 1.4, for example, then you're talking about this. You're talking about having further up into the conduction band, further than the conduction band H. The H is here. H is the tubing, the cliff. Then you have like 0.3 eV, more or less, extra energy supplied to the electron. What's going to happen next is electrons excited into the conduction band are going to thermalize back to conduction band H. It's going to drop down in split second. This is called thermalization. Thermalization, and energy is released in the form of heat or phonon, right? Thermalization process. So it's going to go up, it's going to be excited, and then it's going to thermalize in a split second back to conduction band H before it recombines again, right? So good. So we've got some background already. So result from the properties of the material based upon its atomic structure and atomic properties. To relate the band gap into wavelength, so you can always convert the band gap to wavelength. I believe you've learned this one last time. So if you're talking about micron conversion, you can use this equation where your wavelength in micron equals to 1.24 over the band gap of the material. So if you plug in silicon 1.12 as your EG, let me press the calculator. 1.24 divided by 1.12, you're gonna get 1.107 micron. So that means the wavelength of the silicon, the cutoff wavelength, will be about 1,100 nanometer or 1.1 micron, right? So you can try for zinc oxide, for gallium arsenide, for indium phosphide, and some other semiconductors, and see where's the cutoff wavelength for light absorption neutron. We're going to learn about light absorption neutron. So regular structure, that is the crystalline lattice, is a principal factor to determine the properties of a semiconductor material. So both mechanical, electronic, and other properties, in fact, right? So the crystallinity that we learned last time will affect the properties of the material and eventually the properties of your semiconductor devices, right? So that's why, for example, if you want to relate this to silicon, so silicon, we have learned about crystallinity, right? So if you learn about, if you talk about crystalline silicon, poly or monocrystalline, so poly, oh, ada sedang menunggu, I'm sorry. So thanks for letting me know. Okay, thank you, Isaac. Should put this on the top. Okay, I'll just put this on top. Sorry for waiting time. Hold on, yeah, let me readjust so that I know who else coming. All right. Okay, sorry for that. Yeah, back to the crystallinity. So if you look at silicon, for example, we've learned about amorphous, you've learned about crystalline. So if you talk about polycrystalline silicon or a monocrystalline silicon, the band gap is 1.12. So on the other hand, if you talk about amorphous silicon, the band gap is about 1.8. So band gap of amorphous silicon is 1.8. So from here alone, you can already see the difference or the effect of crystalline lattice or the crystallinity towards the properties of your band gap, at least, right? Which will later determine your absorption and blah, 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 many more, right? So polycrystalline and monocrystalline has 1.12, whereas amorphous usually has 1.8 electron volt. So they are silicon, they are same silicon, but then the crystal structure is different. One is amorphous, which has 1.8 eV, and the other one either polycrystalline or monocrystalline, which has 1.12. So that's the effect of your crystallinity towards the band gap as a proof. So what is 1 electron volt? Okay, 1 electron volt. So we've been talking about 2 electron volt, 1.12, 3.3, 4.5, 10 electron volt. So what is exactly 1 electron volt? So 1 electron volt is equal to 1.6 times 10 to the 19 joule. If you want to convert it into joule, then 1 EV equals to 1.6 times 10 to the minus 19 joule. So it can be defined as the energy required or energy gain by one electron, just a single electron, with electronic charge of 1.6 times 10 to the minus 19 coulomb, we've learned before in electronic, as it falls through a potential of 1 volt. So this is your electron, for example, in this illustration, and it's falling through a potential of 1 volt. So that will give you 1 electron volt. As a result, you will get 1 electron volt. So the energy gained by 1 electron through this positive potential as it drops through 1 volt. So that will give you 1 electron volt. So that's basically 1 electron, which with the charge of 1.6 times 10 to 19 minus 19 joule times 1 volt. So that will give you 1 electron volt. So then what causes band gap? How do we get band gap in the first place? So when we talk about band gap, we're talking about a semiconductor material with atoms with certain arrangement, right? So when you bring together multiple atoms coming together to form the material, right? So they will interact, the atoms will interact to affect certain properties of the material. So what you're going to have is each atom has its own valence electrons and stuff, right? So the electrons arrangement, then the interaction of the wave function of the electron, interaction of the wave function of the electrons of each atom coming together to form the material will result in a split of allowed energy levels, right? So for example, if you look at this graph at the bottom of this page, so electron energy is on the y-axis and interatomic distance. So that means the distance between your neighboring atoms is on the x-axis. So if you bring the atoms closer and closer and closer, so you're actually going towards the 0, 0 here, towards the 0, 0 coordinate here, or towards the origin. If you bring the atoms together, you are going to the origin, nearer to the origin. At some point where your interatomic distance equals to A, there'll be band splitting. So there'll be band splitting resulting in allowed energy levels of the electrons, right, in each atom, okay, due to the interaction of the materials, of the atoms brought together close enough, which leads to energy. So this band of allowed energy levels is called band gap, right? So that is the result, that is the cause of your band gap. So if you look at energy, you've learned this one, right, in solid state physics. Yep, 307. Energy momentum relationship for a free electron is parabolic in nature. So we know that E is equal to half mv squared, or mv squared over 2 here. And then that can also be represented by p squared over 2m. If you look at if put the mass and v, you replace that, and you can rearrange and you can get the very same thing. So that is also can also be represented as p squared over 2m. And if you look at the x squared, y equals to x squared graph, so it's basically a parabolic, right? It's basically a parabolic. So that gives the shape of the EP graph. So the energy versus momentum, right? So when an electron is moving within a periodic crystal lattice, the atoms of the lattice affect the electron's motion. So we've discussed about the splitting of energy levels now. After the atoms are brought close enough to each other, beyond A, as they move closer and closer to each other towards the origin of the previous graph. So, and then we can have these energy levels which become forbidden or the band gap. So angular wave number, if you want to look into this, I think this one is already covered in solid state physics. You can also represent the K value as 2 pi over lambda or 2 pi p over h. So, alrighty, the presence of the periodic structure of the crystal changes. So, the presence of the crystal lattice changes the velocity and the effective mass of the electrons and holes. So, since we're talking about electrons and holes as the carrier in our semiconductor, so they're going to be affected by the presence of the crystalline lattice or the crystallinity of your semiconductor material. And this results in some change of your value of effective mass of electron and holes for different calculations, for example. So you're going to appreciate this one more as you go through the calculation later on, because we're going to use different value for DOS or density of states. We're going to cover a bit later on, and conductivity of the semiconductor material later on. So as you go through the calculation later on, you'll see that different values are required for different sort of calculations. For example, if you talk about silicon in this case, so silicon in this case, if you want to use the effective mass of electron and hole for density of states calculation, we're going to see later on density of states, you're going to use 1.08. Whereas if you want to do the same calculation but for conductivity calculation, so the value of effective mass will be 0.26 instead. So this is also applicable for hole, right? So band diagram. So what is then band diagram? So band diagram is a simplified representation of energy structure of a semiconductor such as silicon and others. So you can see the illustration on the left and on the left and on the right here. So at 0 Kelvin, so at temperature of 0 Kelvin, all the valence electrons reside in the valence band, and there's no electron in the conduction band. And CB is completely empty, or that means there's no electron in the conduction band at all. And that can be represented by the one on the left here, where T is at 0 Kelvin. So they are all frozen, if you like. So you can only find the electrons in the valence band, and you cannot find anything in the conduction band. But if you supply a little bit of heat to the system or to the material higher than 0 Kelvin at whatever temperature, so there'll be occasional phonon, or you are actually supplying heat to the lattice, which gives enough energy for these valence electrons to be excited into the conduction band, right? Valence band, conduction band. So due to the heat supplied at temperature higher than 0 Kelvin, occasionally some of the valence electron will have enough energy to cross the band gap, right, to be excited into conduction band for conduction. So that's why if you heat your semiconductor material at higher temperature, or at some temperature to be more specific, which is specific to that semiconductor material, you will see that the conduction can take place. Okay, so I'm going to show you some YouTube video later on ELAN. I'm going to upload some video for you to see the effects of the temperature towards the conduction of electricity. So when you talk about semiconductor material, you also have to know about direct band gap and indirect band gap. So have you covered this in your 307 last time, solid state physics? Indirect band gap and direct band gap. Have you covered? Yep, all right. So Amirul, can you explain a little bit apa maksud direct band gap, indirect band gap before we go through? What do you understand so far about both? You can unmute yourself.
Direct band gap tu maksudnya dia angle dia daripada valence band ke conduction band tu dia 90 degree.
Okay, maksudnya dia punya both bands are aligned, yeah, is it?
Yeah.
Okay, how about indirect band gap?
Direct band gap dia punya dia tak align lah dia.
Okay, dia tak align lah. Okay. Alright, okay. Okay, thank you. So
Okay.
how about the examples of semiconductor materials with direct and indirect band gap? Anyone? Sari Izyani? Any ideas? What are the examples of semiconductor materials with direct and indirect band gap? Sari or Izyani? Anyone? Juaria? Gallium? Semiconductor? You mean semiconductor? Rafai? Juaria, what do you think? What are the examples of semiconductor materials? Okay, Rafai, you said GaN, gallium nitride. So GaN is direct or indirect? We're going to see later on what is the definition, by the way, but just to recap what you've learned before in your previous course. How about GaN, Rafai? Kavina or Juaria? What do you think? Any examples? Okay, you said direct band gap. Okay. Rafai said direct. Alia said indium arsenide, direct band gap. Okay. How about others? Any other examples before I go through the content? Gallium arsenide. Okay. Alia, gallium arsenide is direct or indirect? GE. Okay. Darina said, okay. Alia said direct band gap, gallium arsenide. Yes. Good. Darina, germanium is indirect. Okay, good. Thank you. So let's go through what is actually direct band gap and indirect band gap. We can see that we have generally we have two different types of band gap, whether it's direct or indirect band gap, and these have a tremendous effect to the properties of the semiconductor material, right? So let's see what is indirect band gap. So Amirul, if you can relate to this, to what you said just now, this is considered direct or indirect band gap, Amirul, based on what you explained just now. This is considered a line or not line?
Not line.
Tak line, okay? Tak line. So cuba tengok apa yang tak line. What is not a line exactly? What is not a line, if you can explain? So the alignment here, okay, go ahead, Amira.
The conduction band
Connection band
and covalent band. Covalent.
valence.
And valent band. Valent.
Okay. So the alignment here is about the alignment of conduction band and valence band. So that will determine whether you have direct or indirect band gap. To be more specific, so it's about the alignment of, let me draw on this, it's about the alignment of the bottom part, or the minimum point of conduction band to the maximum point of valence band on the x-axis, right? On the x-axis, to be more specific. So it's about the alignment of the minimum point on conduction band and the maximum point on valence band on the x-axis, on the momentum axis, right? So we have EK diagram here. Momentum, so the E here is the energy, so the y-axis is the energy, and the K here is the momentum, right? So the alignment refers to the alignment of these 2 points. So they are not aligned like that on the x-axis. They are sitting at different coordinates on the x-axis, so therefore they are not aligned. So when they are not aligned, they are called indirect band gap. So in this case, it's indirect band gap, right? So why here? Because, so that's the explanation, because the minimum point on your CB is not aligned to the maximum point on your VB on the x-axis, right? So that means if the valence electrons need to be excited from valence band to conduction band, so that's how it's going to go. So it's going to need some energy on the y-axis in order to be excited on the y-axis. But if you go on the y alone, it couldn't reach the bottom of the conduction band, right? It's still, if you're driving a car, you want to go to the right, you don't want to go to the northeast, right? You don't want to go to the north, you want to go to the northeast, you don't want to go straight. So what you have to do is you have to take the road ahead, right to the north, and then at a traffic light, perhaps you have to go to the right in order to reach that particular destination, a park or a restaurant or something. You cannot just go straight because you'll miss the restaurant. So that means we need to have the right energy to be able to get to that y-axis. You have to get the right energy to get there at that point, and then you have to steer to the right in order to get to the destination. So in this condition, you need the right momentum from your crystal in order to reach the bottom point of your conduction band. Then only, so you need E here on the Y, and you need K here on the X in order to reach the bottom point of your conduction band. Then only the excitation will happen, right? So on the other hand, if you compare this to direct band gap, for example, if you can draw this EK diagram as well, EK. So if you just have one like that, that's the bottom point, that's your bottom point for the direct band gap. So which one is easier for the excitation to take place? The indirect band gap or direct band gap? If you're driving, is it easier to drive straight and arrive, or drive straight and steer to the right in order to arrive? Which one is easier for you as a driver? The right, right? Straightforward. Yeah, straightforward. So, of course, it's easier to just drive straight. You can even, close your eyes and, go on AV mode, autonomous vehicle, and then go straight, arrive after 10 kilometers. Straightforward. So that's exactly what happens to the valence electrons. So for it to be excited, so it has to just go straight in order to reach the destination, which is the minimum point on the conduction band in order to be excited. So then only the excitation is considered to take place. On the other hand, if talking about indirect band gap, you need to go straight and then you need another step. So in this case, you need E and K to be able to reach your destination. But for direct band gap, you just need the right energy on the y-axis without any assistance from your phonon, from your crystal momentum on the x-axis to be able to reach your destination. So that's why in semiconductor, excitation is a lot easier to take place in direct band gap. So not indirect, in direct band gap, two different words. Indirect band gap semiconductors in comparison to indirect band gap semiconductors, right? So it's a lot easier to excite electrons in direct band gap in comparison to indirect band gap, right? So just like the driving analogy, right? It's what we call clear enough for you to understand the difference in the excitation. And this will affect the properties of your semiconductor materials. So let me go to a little bit more before I stop. So let's go to the definition. So we discussed a little bit just now, and you've shown your understanding already. So direct band gap transition means energy loss in the transition can be given off as E equal HV. Okay, you're talking about, if you're talking about direct band gap, indirect band gap, you're talking about two different directions. First one is excitation of electron from valence band to conduction band. So we're talking about going up. So this is normally required in solar cell. We're going to see later on. I'm going to tell you again why is it so. But this means that for a solar cell, for example, if you have photons from your sunlight, this is your sun, for example. So these are your photons coming to your semiconductor. So if you use direct band gap semiconductor as your solar cell, what you need is the right energy level, the right energy from the photon in order to cross the forbidden gap, just like what we discussed on the Penang Bridge just now. You just need the right amount of fuel to be able to get from my house to USM, for example. Done. Simple, right? So that's going up. So that's about excitation from valence band to conduction band. On the other hand, we're going to learn later on about another process, another natural process, which involves electrons going down. So we've discussed a little bit on the thermalizations now, where you have extra energy and the electron that is excited further up into the conduction band will naturally thermalize back into conduction band edge. So now it's going down. So going down is another natural process as well. So in direct bandgap material, not indirect, indirect bandgap material, semiconductor. So when the electrons are going down back to conduction band, the energy difference or the energy equals to the bandgap will be given off as light emission. And that's what you get from an LED like gallium nitride or whatever, or some other direct bandgap semiconductors that can be used as an LED. So when they thermalize, when they're going down back to conduction band, the exact amount of energy is transferred into light emission. Okay, that's why you see light from LED and stuff. So this is used in direct bandgap semiconductor. On the other hand, this is not happening in indirect bandgap because the energy released from the electrons while going down, while thermalizing back into the conduction band, back into the valence band, will be given off as heat instead of light. So remember, in direct bandgap, you're going to get light as your emission. That's how you get an LED, by the way. So you want this to happen in LED because you want to get more emission, you want more emission. So that's why you induce with electrical supply to the LED. You power it up at the right current and voltage to be able to light up the LED. And before you even get the light, you will actually have the emission process as what is illustrated here. On the other hand, in indirect bandgap semiconductor, the energy difference will be released as heat to the lattice, right? So light in direct bandgap and heat in indirect bandgap. So the process here can be both ways, going up, we call it excitation from valence band to conduction band, and recombination, we're going to learn recombination later on, or thermalization if you like at this point, which involve electrons going down from conduction band to valence band and results in either light emission or heat emission. So that's what exactly this slide is all about. Energy loss in the transition. This is about going down, right? Going down from conduction band to valence band, right? So then you're going to get photons emitted. So in solar cell, you absorb photon in order to produce electricity. In LED, is the complete opposite process. You use electricity to produce photons. So it's an opposite process. So a good LED is a good solar cell. So think about this. A good LED is a good solar cell by this mechanism, right? So the energy loss in this transition can be given off as H mu, right? You've discussed this one, or Hc over lambda if you like. That's why you can convert the band gap into the wavelength as what we've done in the previous slide just now, the 1.24 over Eg here, right? So that's how you can choose the correct, what you call the correct value of your band gap in order to get the right color of your emission, right? So you can actually tune the band gap of the LED material, of the semiconductor material as your LED in order to get the emitted light, the color of the emitted light. So it's about the conversion of Eg and lambda in this equation. Exactly this. So let me just finish off that slide and then we're done. On the other hand, in indirect bandgap transition, just like silicon, germanium, for example, silicon or germanium, assistance is required. So assistance here is the K value on the EK diagram. Remember, E plus K for indirect bandgap, just E for direct bandgap. So K is required for electron to change its momentum on the x-axis. So, for example, from intermediate defect state or trap, we're going to learn later on, and the energy is lost. Energy loss is generally given up as heat. So the key here is heat. And the first one is now is the light emission, right? So therefore, generally, for optical applications, direct bandgap semiconductors are the material of choice for the application. So if we talk about optoelectronic application, like lasers, LEDs, and whatever, that is optoelectronic application which involve emitting light. So you need to use direct bandgap semiconductor because it produces light emission. Light emission, right? So you cannot use indirect bandgap. So that's clear. So for example, you can use gallium nitride, or you can use some other direct band gap materials for optical applications, but not silicon. But you have an exemption as well. Silicon can also emit light under certain conditions. So any ideas? Do you know when silicon can emit light, for example? So generally we learn about the physics that says direct band gap is used for optoelectronic application, not indirect band gap like silicon, of course. But under some condition, silicon can also emit light. So under what conditions silicon can emit light? Any ideas? Before we wrap up the session, when can silicon emit light? Yes, silicon can emit light, but not in default condition. It has to be in specific condition. When they are heated at high temperature, really? And nope. Well, it depends on what the high temperature leads to. It's not a complete story. You may elaborate a little bit later in order to get to the point. So I just leave you with that question, okay? Under what conditions silicon can emit light? So tomorrow is Friday, right? So today Thursday. Tomorrow is Friday, and the class will be 10, right? Oh no, no class tomorrow, right? Sorry, I forgot. I used to have classes on Friday. So I just leave you with that question, and we'll continue next week. We'll try to answer the question when we start the class next Monday, 1 to 2 p.m. So go back and search under what conditions silicon can emit light to defy the rule of physics that we just learned today. Okay? Done. Any questions for today? Is it? Yep, go ahead. Haziq, yep.
Yes, saya cepat pandang.
Okay.
Tapi tadi kan ada dalam satu slide kata partially filled.
Okay.
That part saya ada agak confused dengan dua slide tu. Satu slide yang awal-awal yang merah tu.
Ya.
Partially filled dengan yang biru. Yang biru.
Merah dan biru.
Merah dan biru.
Okay. Nanti saya bagi explanation on the example of material with partially filled semiconductor, partially filled band. Okay, boleh?
Okay. Baik.
Alright. Any other question?
No.
So others, how about others? Any other question? So I'll give you the example of the YouTube video as well on the effect of heat to the conduction. Right then, if there's no other question, I'll see you Monday. Okay, I'll see you Monday 1 to 2 p.m. I'll give you some materials on eLearn as well to support the facts that we've discussed today. Right? Tak ada? Okay. Can you follow so far? Is it okay so far? Yep. Okay, that's good. Okay then, so yeah, take care, bye-bye, and assalamualaikum. I'll see you again Monday, inshallah.